Fender performance and life cycle vary dramatically based on the type of rubber used, natural or synthetic, and virgin or recycled, and the compound composition of the rubber. Compound composition has a dramatic impact on velocity factor, temperature factor, and fender life cycle. Pieng's 2002 Guidelines for the Design of Fender Systems highlighted the importance of velocity factor and temperature factor in the design and selection of fenders, and introduced guidelines for reporting and calculating both. But current research into the changing properties of rubber compounds used in fender systems and the move towards non-traditional fillers mean velocity factor and temperature factor are now highly likely to have a material impact on engineering design and fender selection, as well as further implications for the design of other wharf infrastructure. First, let's take a look at velocity factor. Fenders should be tested at realistic berthing velocities to determine actual performance, but it's difficult to test at the speeds fenders will be subjected to in the field. The correct application of velocity factor is highly dependent on the natural rubber to synthetic-based rubber blend ratio and the overall rubber compound formulation. Given the same compression time, a fender comprised of 100% natural rubber will have a lower velocity effect than one composed of 100% synthetic-based rubber. Synthetic-based rubber is commonly used in marine fenders as a replacement of natural rubber to improve physical properties, for example, in high-temperature applications. So it is necessary for manufacturers to understand the effect of rubber compound composition on velocity factor. Velocity factor significantly affects fender performance characteristics and therefore fender system components and the wharf structure. Using velocity factor, performance figures should be adjusted to account for design berthing velocity. In general, we'd expect to see increased reaction force and a corresponding increase in energy absorption. The overall system design will need to account for the increased reaction force and the reaction force loads reviewed against the structural design of the wharf. Temperature factor is another major consideration. Elastic properties are measured by stress and strain behavior and expressed as the modulus of the rubber compound. Specifiers should be concerned about the elasticity of the rubber as it is a measure of stiffness. Reaction force and energy absorption are directly proportional to rubber stiffness, which changes dramatically with temperature and has a significant effect on fender performance. As such, rubber elements for fender systems must be tested to the temperatures they will be subjected to in the field. Failure to do so could have a tremendous adverse effect on the berthing structure. Temperature factor is vital in determining the impact of low and high temperatures on the energy absorption and reaction force of the fender. It plays an important role in both the design of berthing structures and the selection of fender systems. Like velocity factor, temperature factor is highly sensitive to the type of rubber used: natural, synthetic, a blend of the two, or recycled. This will vary from manufacturer to manufacturer. Let's look at the impact of temperature factor and velocity factor using the example of an SCN 1000 E2.5 fender. The rated performance data is shown here. In the field, this fender is going to experience a ship berthing of 160 mm per second initial velocity in a location with a temperature range between 10 degrees and 40 degrees centigrade. Under the extremes of the real operating conditions, the effects of temperature and velocity are summarized here. In real life, reaction force increases by 25% and energy absorption will decrease by 7%. The same fender performs differently depending on the factors applied. The magnitude of the factor depends on the rubber compound used and size of the fender. Both have a significant effect on fender performance under real operating conditions, and subsequently on the design and selection of the system and of the berthing structure. The durability and life cycle of rubber fenders depends on many factors: the type of rubber used, compound formulation, environmental conditions, heat, ozone, operational use, and mechanical damage. Oxidative aging, a process described as the change in rubber properties over time, is one of the main issues impairing the functionality of rubber fenders over their life cycle. The mechanisms that produce oxidative aging depend not only on the degradation agent, oxygen, present in the environment, but also the type of rubber used and any additives used in the compound formulation. We investigated the effect of higher percentages of recycled rubber on the longevity of fenders, using test pieces made from 20% recycled rubber and others made from 75% recycled rubber. Fenders made with lower percentages of recycled rubber had a predicted life cycle of 57 years at 20 degrees centigrade. Those with 75% recycled rubber had a predicted life cycle of just 6 years. It is evident from the study that fenders made of higher percentages of recycled rubber can have a life cycle almost 10 times lower at 20 degrees centigrade. It is clear then that there is a lot to consider in designing fender systems for optimum long-term performance. The selection of rubber compound ingredients is critical. Specifiers and manufacturers alike must understand the impact this formulation has when applying velocity and temperature factor and when considering fender performance and life cycle.